is free, so that it's the minimum energy that you would supply to the electron with the minimum energy. It will be 13.6. So the ionization energy of this tank is 13.6 electron volts. What is the ionization energy of the first excited state? That would be 3 plus 3.4, right? Because when the electron is in that state, it has this much energy. But if you give it 3.4, then the energy is going to be 0, and that's when it just barely breaks free of the electron. You can give it more energy. If the electron is in this particular state, for example, the first excited state, then its energy is minus 3.4 electron volts. What if I shoot a photon on it, and the electron absorbs that photon, and suppose the photon has an energy of 4 electron volts? So what would happen to the electron if its energy initially is going around the proton, right? And then its energy is minus 3.4 electron volts, and then absorbs a photon of energy 4 electron volts. Then what would the energy of the electron be? It'll be what? 0.6 electron volts. And what happens is that the electron takes in the 4 electron volts. It uses a 3.4 electron volts to exit, to liberate itself from the proton, and then the energy that remains, once it's free, is just, 0.6 electron volts. And then it'll be free. It'll just go out. It can be part of, if this is in a wire, it'll be free, and so on. But anyway, I just wanted to say that we have, this looks like a quantization condition with restricted values for n, right? It's something that you've seen. I'm sure that when you took general chemistry, you saw maybe this formula. I don't think you saw the derivation of it, because to get to this answer, you need to consider that and, physics, right? And usually people take chemistry before they take physics. So probably they just gave you the formula, gave you some terminology associated with that, and then they called that the principal quantum number, and then they restricted the values to this, that. So it's something that, this case where n can have only specific values is something that you've seen before, I think, in the context of the hydrogen atom. But it's a theme that shows up again in this other context, in this other topic of standing waves in a string that's clamped at both ends. And there are some questions that you can answer pretty quickly. Fundamental frequency, the second harmonic is twice the fundamental frequency, the third harmonic is 3 times the fundamental frequency. So let me ask you a question that you should answer, or at least figure out the answer in less than 4 seconds. I know some of you like those questions, right? Yes? Okay. MCAT exam type of questions, which I think many of you will take in the future. They tell you, a string is clamped at both ends. They don't tell you the length of the string, they don't tell you the mass spring length. And all they say is that so the string is clamped at both ends. And then they tell you that the fifth harmonic is 250 hertz. So what's the value of the third harmonic? I heard it. That took less than 2 seconds. Are you guys still thinking about it? You want to talk to someone about it? So the fifth harmonic is 250 hertz. What's the frequency of the third harmonic? Is it obvious? No. And you can imagine students like, what's the formula, and what to plug in, what was the length, was this? And they never told you that. If the fifth harmonic is, what did I say, 250 hertz? What is the fundamental frequency? 50 hertz. And therefore, the fundamental frequency is 50 hertz, what's the third harmonic frequency? 150 hertz. No real need to plug numbers into a formula, solve 2 equations to unknowns, or stuff like that, right? So, you want another one? Yes? Okay. Let's see. So a string is clamped at both ends, and they don't give you the length and the mass spring. They don't give you. They just say that the let's see, that the frequency of the sixth harmonic is 36 hertz. What's the frequency of the second harmonic? Good. See, that didn't take too long. 12 hertz. If the frequency of the sixth harmonic is 36 hertz, then what's the fundamental frequency? 6. And therefore, what's the value of the frequency of the second harmonic? That is twice the fundamental. So 6 times 2 is 12 hertz. Okay. So I have some of this in my notes. There is a mathematical way to derive these expressions, where you actually write down an expression for the total disturbance of the string, and you write it as a wave traveling to the right and a wave traveling to the left, and then you add them up, and then you do the math, and so on, and then you end up with the same result. Let's see. Okay, what do I have here? It's kind of cute. You draw these little loops, and then you come up with the answers, right? So this is the fundamental frequency. This one corresponds to the fundamental frequency. This one corresponds to the second harmonic. The number of loops is like you can say, okay, if it's got 3 loops, it will be the third harmonic. If it's got 4 loops, it's the fourth harmonic. So we derive this, right? N can be 1, 2, 3, 4. The speed of the waves, transverse waves in the string, will be given by the square root of 10 divided by the mass spring length. And so you can generalize it like that. And then what are the allowed frequencies? The lowest one is the fundamental, and then twice that is the second harmonic. 3 times that fundamental frequency is the third harmonic. Right? So here you have all the even and odd harmonics. Now, there is a fourth harmonic, there is a fifth harmonic, there is a seventh harmonic, there is an eighth harmonic. So all the harmonics are present. And I made that statement because in chapter 16 we're going to consider the same thing, but instead of a string that's clamped at both ends and you have transverse waves traveling along the string back and forth, we're going to consider like an organ pipe, and then you have sound waves. Right? And then the pipe could be such that it's closed at one end but open at the other end, or open at both ends. So in one case, only the odd harmonics are present and the even harmonics are not in there. So that's why I added this statement here that all the even and odd harmonics are present. And then this is just a formula. I don't want to talk about that. So the quiz, you're taking a quiz this Thursday, correct? It'll be on chapter 15. And maybe you can answer the question in the quiz in less than a minute. Maybe. I mean, there are 2 ways of doing it, but one of them is probably less than that, but we'll see what happens. Okay. And by the way, this, just the terminology, like this point here in the string, as this string vibrates up and down, up and down, up and down, right? That point is always there. That's called a node, like nothing. Thing never goes up or down. That's called a node. Now, and then that's another node. And then, the middle of the string, over here, between this node and this other node, in the middle of the string, that's the part of the string that will undergo the biggest displacement, above and below. And so this is called the antinode. Antinode, node, antinode, node, antinode, node. Okay, so sometimes they'll tell you the distance between 2 adjacent nodes. What if I ask you that the distance between 2 adjacent nodes is 5 millimeters, then what's the wavelength?
2.5.
So the distance between two adjacent nodes is 5 millimeters. What's the wavelength? How much? 10 millimeters, correct. So if you have something like this, that's a picture, let's say t is equal to 0, and then half a period later, it's going to look like this. Right? So if I tell you that the distance between two adjacent antinodes, right, that's an antinode, and this is another one. If I tell you that this is 5 millimeters, that's an anti that doesn't want to be an anti. Thank you. Then, well, the wavelength would be like, the wavelength is this. So this is the wavelength. So if that's 5 millimeters, this is also going to be 5